We have once again reached a point, that's where I'm reading, where we can apply what we've learned so far to some interesting word problems, applications. Here are the basic steps for solving these word problems. Read and understand the problem. Draw pictures. Introduce notation. Determine the variable to be optimized. Find the objective function. Express the variable to be optimized in terms of the other. Use the given restrictions information to express the variable to be optimized in terms of one single other variable. Use the methods of this section to find the absolute max or min of your function. Pay attention to whether or not your function is defined on an open or closed interval. Okay? So this all doesn't make sense until we do an actual problem. So I'm going to look at this first one that I have in my notes. It says, find the maximum area of a rectangular pen if you have 100 feet fence. Now in my video I went through and showed you the different ways that you can have a 100-foot fence. Now honestly, how many of you watched the video? It's okay if no one did, but so you understand that there's many different ways you can have a pen out of 100 feet of fence, right? And each one of those has different areas. So what shape gives you the maximum area? What dimensions? What do you think it is? 10 by 10, a square, right? A perfect square. That would make sense, right? That would give you the most area, 10 by 10. But is that using 25? Is that going to give you 100? It's saying 100 feet of fence, we're saying 100 feet of fence. 25 by 25. I think you were thinking I have 100 square feet of area. 25 by 25. Should give us the most area, right? Should be, but it's a question. So let's try and do this with the calculus, all right? Find the maximum area of the rectangle you want to have. So I'm going to read it. I kind of understand it. Do you understand it, what we're looking for? What are they asking for? The maximum area. So our final answer should be an area, shouldn't it? Draw a picture. Well, a general picture of a rectangle looks like this. Right? It has a length and it has a width, or we call that height, it doesn't matter. That's the general picture. Now, don't mistake this with like related rates where we did a general picture in an instant in time, because we have no instant in time anymore. Time's not running in the background. It's just we need to build a rectangular pen. So I've drawn a picture, I've introduced some notation. Determine the variable to be optimized. What do they want optimized? So think about when we talk optimization, think maximum minimum, max min. What do we want the max or minimum of here? We want the maximum area, right? So the thing that we want to optimize is the area. Okay, we want to optimize the area. Get the most area possible. So come back down to my picture. Do you have an equation that relates that rectangle to area? Length times width. So I'm on step 4 right now. Express the variable to be optimized in terms of other variables. Right? Area is equal to length times width. Now let's look at number 5. Use the given restrictions or the given information in the problem to express the variable to be optimized. So that means to express which variable? A, So they want us to express A in terms of one single other variable. Right now, in order for me to know the area of a rectangle, I need to know the length and its width. But I'm supposed to use some information that's given to me in the problem to get it to be only in terms of L or only in terms of W. So what have I not used in this problem? I have 100 feet of fence, right? I have 100 feet of fence. Haven't used it. Well, how does that relate to my picture? If that means the entire distance around this thing has to be 100, right? That's right. So that means that 2L plus 2W equals 100? Yes? This is known as a constraint. What we are trying to come up with here is what's called the objective function, which I'll write down as soon as we get it. So it's like we can make any rectangle we want. L and W can be anything, but as soon as I tell you you have to use 100 feet of fence, I've constrained you, haven't I? I've changed what's possible for you. So that equation is my constraint in this problem. And what I'm going to do is I'm going to solve it for either L or W. So divide everything by 2 first, right? And then 50 minus W. I could have solved for W. I just chose L because I kind of looked up at the equation up there. A equals L times W. It wouldn't matter if I replaced L or W. It'd pretty much look the same. So now rewrite A up there. What would it be? What is L? 50 minus W times W, right? So area equals, I'm going to distribute that W through 50 minus W squared. Do you all agree with that? And now I'm going to add one more thing. I'm going to write A of W equals 50W minus W squared. All I did by putting A of W in there is I've stressed the fact that now A is dependent upon W. As soon as you tell me what W is, I can tell you the area. I don't need to know L. Oops, sorry. I forgot to mute that. I can't believe that man's calling me right now. I'll tell you all that story if I have time. Can't get people to do good work on anything these days. Okay, so putting the W in parentheses there just stresses that this is a function of W. That's what I'm going to write underneath it right now. This is the objective. Now, what we want to know, remember, what were we trying to optimize here? The area. We're trying to find the maximum area, and I now have a function that represents the area, don't I? It's a function of a single variable. Well, that means I should be able to find its maximum, shouldn't I? How do we find the maximum of a function? Well, it depends on if it's on a closed interval or an open interval, right? It depends. So how can we determine if it's closed or open? What's the variable in this problem? W. So the question is, can you put a restriction on W or not? Is there a maximum that W can be or a minimum that W can be? What would the smallest W could be? Sorry, that's kind of weird to say that. Imagine that you're out there and you got 100 feet of fence and you're like, all right, let's build a rectangle. Right? Have you ever seen like those rolls of fence, like the chain link fence or something? Let's say we have a 100-foot roll, right? Couldn't we put off our picture, right? This is LLW. we have to first determine, let's say, what's L going to be? Or what's W? We could choose. Let's say W. We could say, let's let W be 50. Then you would have the whole fence, wouldn't you? You would take it and you'd cut it in half and 50 on each side, and then you'd say, shit, I don't have anything left for L, right? That's one way we could do it. But you wouldn't even have a rectangle, would you? So 50 would be the absolute biggest value you could ever use for W. What would be the smallest you could use for W? 0. And then use the rest for L, right? No one would ever do that, but the thing is, can we fix our W between two numbers? Yes. So we could say 0, and you can't say 100, you have to say 50 here. Does everyone understand why it's 50? Because W represents the two sides. If you say 100, right? If this right here was 100, then come into this equation right here, your constraint, and replace it with 100, and what would L have to be? Negative 50. But if you put a 50 in there, then L can be 0, and that's okay, right? Yes. Because we need a closed interval. Okay? Basically, we would be making a fence making a rectangular pin that had no length to it if we did that, which would be absurd, but we want to include 50 because it makes the closed interval happen. Yeah, I mean it's physically it's kind of weird. It has no width, which lines don't have a width, right? Lines are, from point to point there is no width, just like a single point has no width to it. Okay. All right, so do we have a continuous function on a closed interval? All right, this is a continuous function. It's on a closed interval, and therefore we'll do it what we call the closed interval method to find it. So we'll need to take a derivative, right? A prime W equals 50 minus 2W, right? What are we supposed to do with that? Set it to 0, find out where it doesn't exist. If it doesn't exist, I don't have to worry about, right? Because it's actually a linear equation, or linear function at this point. And set it to 0. You get W equals 25, right? So that is a critical number. Does it live inside of our interval? Yes. Okay? So all I have to do now is evaluate the original area function there and at the endpoints, right? There and at the endpoints. So I need A of 0, A of 50, those are my endpoints, A of 25. I think those are pretty easy to plug in, right? You should get 0 if you plug in 0. You should get 0 if you plug in 50. And you should get 25 squared if you plug in 25. So it's pretty obvious what the maximum area is going to be, right? Where it's going to come from? 25. So they asked for the maximum area, right? But in a problem on a test, I might not ask you, what's the maximum area? I might ask you, what are the dimensions of the pen that give you the maximum area? So you would have to, from this, you know that what? W was 25, right? Which means that L must be, and you would go back to the equation you have for L there, plug in 25, and in this particular case, L would be 25 also. Right? Okay. Now this is about as easy as it's going to get right here. It's about the easiest problem that we'll ever do for optimization.
Do all these have constraints?
They all will have a constraint. They just won't all have closed intervals. Yep. And anyone who's taking Cal 3, who are my Cal 3 people? Okay, a few of you. This will extend into functions of, where you have functions of two variables. So where you get like three-dimensional surfaces,